Next, we have the European Space Agency, ladies and gentlemen. He is the Advanced Manufacturing Engineer in the Materials and Processes section. He supports development of promising advanced materials and processes for space and application. Ladies and gentlemen, it's my pleasure to introduce Advenit Makaya. Round of applause, please, from the European Space Agency.
Thank you very much, and thank you for being here. I will give you an overview of what we are doing in additive at the agency for the last 15 years or so. So some very quick words about who we are, about 50 years experience, 22 member states all over Europe. And our mission is to provide for and promote for peaceful purposes the cooperation between European states for space research and technology and space applications. And we do this through a broad range of activities. We are actually one of the few space agencies which have activities in all these fields, from science to telecommunications and technology development. These are our locations, and I'm located in the ESTEC, the technical heart of ESA, which is in the Netherlands, in Noordwijk. And my section, the Materials and Processes section, supports the ESA projects, the ESA missions in terms of materials and processes. We also promote the development of advanced technologies in materials and processes, and we act as a certification authority, especially for electronic processes. In terms of materials and processes for space applications specifically, we have several very specific challenges. We need low weight, as our aeronautics colleagues, but we work with small production series, typically 1 or 2 or just a handful for our satellites or spacecraft. We need high reliability. When you send something to space, you cannot go and repair. And we have a rather limited range of manufacturing processes which we can count on. So additive manufacturing was thought of something that could address those specific challenges, and my colleague Laurent Pambaguian in particular started looking into it in 2005 with a small study with what was at the time EADS, Innovation Works, looking at the advantage of using direct metal deposition for building parts for space. On the right, you have a part which is a water on-off valve, which is on the Columbus Laboratory on the International Space Station. And my colleague looked at replicating the design, but changing the material from stainless steel to titanium. He managed to reduce the weld, eliminate the weld in this part, and achieved a 40% mass reduction. So through these very preliminary studies, we saw a very big potential for space hardware, for additive manufacturing, but this was rather limited because we were applying conventional designs to additive manufacturing. And working through it, we came to the realization that additive manufacturing exploits its full potential when you actually design for additive rather than replicating the conventional designs with additive. So these are some examples. On the top left, you have a radio frequency filter where we change the geometry to curved internal surfaces to optimize the coverage of the internal silver coating, which is used for RF properties. And we also achieve a 50% mass reduction by topology optimization. On the top right is engine nozzle, and we use the lattice structure on the outside in order to optimize the thermal exchanges and the thermal behavior of the nozzle. On the bottom left, it's a revisit of the design of a tropomy mirror, which we use in the Sentinel-5 satellite, where we change the material from aluminum to titanium, so actually going to a heavier material. But by topology optimization, we managed to reduce the weight of the part while keeping the same performance. And the one on the bottom right is actually exhibited here in the exhibition area. It's a radio frequency resonator, where we looked at reducing the number of parts to just one, and avoiding passive intermodulation effects by optimizing in particular the coverage of the internal silver coating. So that was a successful demonstration of designing for additive. So based on these preliminary studies, we ramped up the complexity and the collaboration with industry in order to demonstrate some products which use the principle of designing for additive. This is also a part which is exhibited here. It's a sense sensor where we optimize the volume and the mass of the casing of the sensor by using selective laser melting in these cases. And we replace the printed circuit board by printing directly the tracks onto the base plate using aerosol jet printing. It was not completely successful, but it's a demonstration of the feasibility of additive to reduce the complexity of a part. This was a very successful campaign performed with our partners Airbus Defence and Space a couple of years ago. We demonstrated the first successful firing of 3D printed platinum-based thruster. So this was a platinum rhodium alloy, and this first in the world success was actually allowed by mastering different steps of a rather complex chain of processes, from powder manufacturing for these very expensive and rare materials, optimizing the additive manufacturing process parameters, and also the post-processing. And another example, which is more recent because it's still ongoing, it's from our Future Launchers Preparatory Program. We are designing a bracket for the upper stage of the Ariane 5, which hopefully will also be incorporated in the Ariane 6 design. And here again, topology optimization to reduce the mass, and validation qualification approach based on topology optimization. So how the design of the part can help in the future qualification. So through these studies, we realized that additive manufacturing is not a process, it's actually part of an end-to-end chain of processes, the same thinking that ITP has just presented. It starts with the design, so you have to take into account design limitations, supporting structures, actual build volume limitations, and so on. And this is where the experience lies. This is where a lot of your R&D costs are, in thinking the design of the part, because it will pay off down the line in terms of manufacturing and qualification. After design, you have material supply, the powders. It's very important because whatever defect you have in your powder, you will find in your final part, and this will affect the performance of your product. You need to understand the properties of the powder. You need to be able to trace the powder from the supplier to your final part. We don't have as yet reuse or handling specifications for powders, and we also tend to use materials used for conventional processes like casting, rather than developing materials specifically for the properties of additive manufacturing. At the bottom, you have a very interesting example which we published earlier this year, where we found inconsistencies in mechanical tests, and our powder screening processes couldn't tell us what was wrong. And then looking at the fracture surface, we actually noticed some small tungsten particles, and doing non-destructive testing of the samples, we also identified tungsten particles. And it was all traced back to the machine which had been used just before our parts to produce tungsten. So it was all about the cleaning of the machine, and that's something that you couldn't screen when we looked at the powder itself. So our recommendation is really one material for one machine. And the process itself, of course, is very important in terms of scanning strategy, in terms of hull and core scanning, having different islands rather than printing a part in successive steps. The atmosphere is very important to control. Process monitoring is a very active field in additive manufacturing, being able to spot the defects as we build, and of course the repeatability. After processing, you have the post-processing, so you need to clean your part to improve the surface. We have different studies in this field. This is a picture from one of our studies where we use different post-processing techniques on the surface, grinding, shot peening, polishing, in order to achieve the roughness that we need for our applications. In terms of post-processing, you also have potential defects caused by the agents that you use for cleaning the parts, which can get stuck into cavities in your part. In this case, you have ceramic ball and a steel ball, which were used to pin the surface of the part, which ended up being in the part. So you have to design your part thinking about the different steps that will be needed to arrive to the final part. So thinking, if I have a cavity in this part, will it affect the possibility of trapping some pinning bolts and so on? And then qualification, which is something we are very involved in at the agency. Of course, you have challenges in terms of non-destructive investigation capabilities. Complex shapes are difficult to investigate. We have to think about product assurance requirements. Which one do we use for qualifying a part to space? Materials allowable. What are the range of properties at the start, at the sample level, which will tell you that your part will do the job when it is in actual use? And actually, big companies involved in additive manufacturing have put a lot of effort into material characterization, trying to map a range of properties which you get using this machine, that set of properties, and so on. And that, of course, is quite expensive, but at the moment, we don't see a better way of ensuring the reliability of parts produced by additive. So as I said, it's very dependent. The quality of the part is very dependent on who does it, which company does it, which people they have inside, their level of experience, their understanding of the challenges of the processes. So that's very key to surround yourself with the right people, and very key to talk to each other, to learn from each other, the same way we have the opportunity to do it here. We are preparing a standard, an ECSS standard for additives for space. The working group should kick off later this year, and we'll come up with hopefully a more precise set of specifications for putting additive parts into space. All these collaborations with companies have led us to harmonization work, harmonization roadmap, which we kicked off in 2014, which involved discussions with more than 700 experts from 26 countries. And this roadmap was divided into different aims. The first one is space products. So we identified a range of space products which could benefit from additive processes and the building blocks that are needed to achieve these products. We have the various aims which are associated to the steps which are described in the end-to-end process: design, raw material supply chain, process, post-process qualification, and the standards. Sorry. Sorry, I need to go back. Yes. So this is an example of a space product, if it comes. Seems to be a bit of a delay. Yes, okay. This is an example of a space product in our roadmap. Here it's for structures application. So on the top you have 3 products which we identify: a shock-absorbing structure, primary structures, because for the moment additives is mostly used for secondary structures like brackets, and also large aluminum and titanium structures. And at the bottom, you see the building blocks in terms of what technology development activities we need to do in order to arrive to these products. And we try to quantify the effort in terms of finances to allow these building blocks. We have opened last year or earlier this year the Additive Manufacturing Benchmarking Center. It is located in the Manufacturing Technology Center in Coventry in the UK. And this center is open to ESA projects, but also to industry. So any one of you in your companies, if you need expertise in terms of introducing additive manufacturing into your portfolio of products, if you want to have guidance into developing a certain prototype, for example, advice on powders, materials, processes, post-processing technique, machines, you can contact us and we put you in contact with our benchmarking center, who will guide you with their expertise and their equipment through the study that you want to perform. They also do failure investigation, and they publish a newsletter about the various studies that have gone through the benchmarking center. So you can contact me or one of my colleagues to benefit from this facility. Then going through the various technology development activities of additive, we realized that if you consider additive at the system level, for example, you think about the mission to establish a lunar settlement, then additive can really impact the way the mission is conceived. For example, if you allow in-orbit manufacturing of spare parts, for example, on the ISS, or if you allow manufacturing on planet of infrastructure, landing pads, habitats, then you can possibly reduce the amount of material that you bring from Earth. So you can use smaller launchers possibly and reduce the cost of mission tremendously. If you manage to build parts in space and not on Earth, then you have to dimension your parts only based on the level of mechanical solicitations that they will see in space. So you can remove the need from dimensioning themselves to the launch load, so you can make smaller parts lighter and so on. So thinking at system level can really affect the way a mission is conceived. So having witnessed this tremendous impact that additive manufacturing can have, we thought about other techniques or other processes which could provide a step change in terms of performance gain, in terms of reducing material waste, in terms of reducing energy consumption. Here you have some examples in solid-state joining, so friction stir welding on the left for a tank, or rotary friction welding from aluminum to a titanium tube. So we try to map advanced processes which could provide similar benefits to additive manufacturing. And that led us to start what we call the Advanced Manufacturing Cross-Cutting Initiative within ESA. And this initiative is aimed at identifying, as I said, game changers in terms of manufacturing processes, which allow design freedom, performance improvement, cost reduction, reduction in lead time, and maturing those technologies into high-performance press products. So this cross-cutting initiative has started late last year, and we have a compendium of activities which is open for bidders to propose their services. And the way the program is structured is that we look at different processes in dark blue, different materials which these processes can be used on, and cross-cutting fields like verification, like standardization, like simulation, which will allow benefiting from these technologies. And the same way we looked at additive manufacturing at system level in order to change the conception of missions, we have started to look at advanced manufacturing processes at system level, how they could affect the way the mission is conceived and the performance of the mission. So we did that last year in a concurrent design engineering study where we brought different experts from materials, propulsion, systems, electrical engineering, and in case studies analyze how changing the thinking in terms of design can help harness the power of advanced manufacturing techniques. I will end up with this page from our compendium of activities. There are new activities now, and if you contact us, you can get a list of the activities you can potentially bid on to help progress the advanced manufacturing techniques. Thank you very much.
Thank you very much. Fascinating.